Hi guys, welcome to another video. Today we discuss longitudinal waves. So the scenario goes as follows. It says consider the diagram below. So before we answer the questions, I want us quickly to discuss the properties of a longitudinal wave as well as the definition. So let's have a look at the following clip. So we can see we have a longitudinal wave given in orange, and you can see that the dotted line is the equilibrium. That red line is called a particle. So it's one of the particles, and you can see the particle is vibrating from right and then it's moving to the leftward direction. So in essence, the particle vibrates around the equilibrium position. But let's look at the wave itself, the orange part. You can see that it's assuming a position from left to right. I want us to look at the compressed parts where it's squashed together. You can see it's moving from left to right. Those squashed parts are what is called compressions, and the parts where the particles are spread out is called rarefactions. So these are the properties, and the distance between two compressions or two rarefactions is called the wavelength. So let's answer the questions. So the first question says, define the term longitudinal wave. So a longitudinal wave is a wave where the direction of the vibration of the particles is parallel. This is the most important keyword to the movement of the wave. So the next question says, write down the name of the labels A, B, and C. So if you look at the schematic, you can see that A is what we call a rarefaction. It's where the particles are spread out. And then B is what we call a compression. A compression is where the particles are closely grouped to each other. And then this distance here between two rarefactions or points on the wave that are in phase is what we call the wavelength. So the distance between these two compressions is also called the wavelength. Thank you guys for watching. See you in the next one.